So in our last video, we found vector AB and vector AD. We got 438 for AB and 263 for AD. And we found out earlier that AB was negative, it's under compression, and we found out that AD was under tension, so it's positive. So as you can see, we've updated our free body diagram. Now that we've done with vector A, we've done our pin joint, let's go ahead and start at our roller joint. So let's find all the forces, the vector forces at joint C. What forces act on joint C? Well, we know Ricky does, well, let me get my right color here. Ricky, which is 150 pounds. We know DC is pulling C to the left. And we know vector BC is pushing down and to the right. And so we're looking for these unknown forces at joint C. Well, we need to find BC. And we need to find DC. And to solve these, what we're going to do is we're going to say, well, the sum of all forces equals 0, both in the y direction and the x direction. So let's start with the x direction. Let's say sum of all forces in the x direction equals 0. Let's also say the sum of all forces in the y direction equals 0. Well, what are my forces in the x direction? Okay, well, we know DC is going to the left, so that's an x component. So vector DC. And there's only one more force going left to right, and that's BC. But not all of it, it's partly going downward, so we're only caring about the x component of BC, BCX. And actually, let me get rid of this arrow here that I put over DC. That's going to confuse you in a second. I was just calling it vector DC, just to give it its proper name, or like down here. But I don't want you to think of these as positive or negative. You don't say BC is going to the right, so it's positive. DC is going to the left, so it's negative. Instead, just think of the direction it's going. So DC is going to the left, and BC is going to the right. And know that all of your leftward forces have to be equal or cancel out all of your rightward forces. So we can say DC equals BCX because they have to cancel out. Well, how do I know that? Well, I know that C isn't rolling away. It's not going left to right. It's not falling apart. So I know they have to be equal. They have to cancel out. What about my forces in the y direction? Well, we have Ricky. Ricky's in the y direction, 150. And I also have BC is going downward. But not all of BC. Some of it's going to the right, so only the y component of BC. I'm going to go ahead and put a divider here. I moved this a little bit to the left so we have some room to work. And this divider is just to tell you that these are two different equations. But again, I don't want you to think of these as positive or negative. Instead, I want you to look at the direction. Well, 150 is going up, and our BCY is going down. And all of my upward forces have to cancel out all of my downward forces. So what does that mean? Well, that means my upward forces have to equal my downward forces. So in other words, 150 is BCY. So with this, knowing that BCY equals 150, we know everything we need to know to solve for DC and BC. I'm going to go ahead and draw vector BC here. And I'm going to go ahead and give it its y component as well, which is 150 downward. So BC in the y direction is 150. And we also have a BC in the x component as well, an x component of our vector BC. So BCX, which we don't know yet. But I can translate it down here to make our little imaginary triangle to kind of picture what this is doing. And as you'll recall, we found this angle earlier, theta 2. We found it to be 29.7. 29.7. So now we can go ahead and solve for BC. So we know the angle, we know the opposite, and we're looking for the hypotenuse. Opposite and hypotenuse is sine. So the sine of our angle, 29.7. Well, that's equal to opposite over hypotenuse. We know our opposite is 150, opposite to our angle. And we set that over BC. Well, to solve for BC, I'm going to cross multiply and divide to make my life easier. I see 1's going to multiply by 150, and then I'm going to divide by the sine of 29.7. So I pull out my handy-dandy calculator, and I type it in. I say 150 times 1. Well, 150 times 1 is just 150. And then I say divided by my other number, which is, not 2, the sine of 29.7. What do we get? We get BC. BC equals 302.7, or basically 303. So it equals 303. And so let's go ahead and solve for BCX then. Well, BCX is adjacent. Now remember, we can use sine, cosine, tangent, or Pythagorean theorem, a squared plus b squared equals c squared. But I'm going to use cosine because I just find the hypotenuse and I'm looking for the adjacent. So the cosine of our angle, 29.7, is equal to adjacent over hypotenuse. Well, adjacent is BC in the x direction, our x component of BC, and our hypotenuse, what's the hypotenuse? We just solved for that. It's 303. So to figure this out, I'll put this over 1, and I'm just going to cross multiply and divide. Well, I can see 303 is going to multiply by the cosine of 29.7. I'm going to divide by 1, which won't change anything. So I pull out, that's the wrong button, I pull out my calculator, sorry about that, and I type this in. Well, I say, okay, well, 303 times the cosine of 29.7. And for our BCX, what do we get? We get 263. So BCX equals 263. Well, we said earlier that BCX equals DC. So therefore, DC is also equal to 263. Well, hold on, Mr. Anderson. 263 looks familiar. Didn't we just get that over here for 80? Well, yeah, and that makes sense. Because if D's pulled to the left, 263, then D needs to be pulled to the right, 263. Which means C is being pulled to the left, 263. So we kind of already knew that. Because math.